In this video, we take a look at section 9.5 dealing with alternating series. So far we have telescoping, geometric, p-series, integral test, and our comparison tests, whether it's direct comparison or limit comparison test, and we'll use some of those in this section. Here, we're always trying to relate things back to those easy series, those p-series and geometric series if we can. They're easy. We know the criteria for convergence and divergence. Alternating series, there is an alternating series test, but an alternating series is something like this. Say, if I have the series minus 1/2 to the power n, yes, that's indeed geometric, but also I notice that this series, when I go out a couple terms, I'm raising minus 1/2 to higher and higher powers as I go. These terms are going to change sign every other term. Right? This is an alternating series. This is what it means for a series to alternate. Okay, and all it is just when each term has an opposite sign, each term has the opposite sign of the previous. Okay? So when I go out, keep going out term by term, I should see signs alternate, and that means that all the even terms are positive or negative, vice versa, or all of the odd terms are negative. Okay? And that's what it means to have an alternating series. Now there's a test that works specifically for these types of series. I don't have to do that test for, like I said, this initial example here because it's a geometric series. I know that criteria already. But let's write down that test here. The alternating series test. It goes something like this. Let C sub n be positive. The alternating series, either one of these two forms, minus 1 to the n of C sub n and minus 1 to the n plus 1 of C sub n. All right? Each of these is just describing where the evens or odds are negatives. Right? For the first one there, this is when all the odds are negative, and for the second one, that's when all the evens are negative. Okay? For this test, we use this C sub n. Okay? This alternating series, whichever form it's in, converges when the following conditions are met. The first is that the limit as n goes to infinity of C sub n is 0. Okay? And it's important to note that I'm not taking a limit of a sub n. Okay? So this is not the limit, this is not the nth term test. I'm just looking at C sub n here, where a sub n is the entire thing inside of the series. It's the entire nth term. I'm just looking at the little guy kind of next to the part that makes the series alternating. Okay. Same for the second condition, but this one's a little different. C sub n plus 1 has to be smaller than C sub n. That's just another way of saying that this has to be a decreasing sequence. C sub n has to be decreasing. Another way we can look at that, I'll do some examples here where I actually look at a term-by-term comparison. That's what this is called, term-by-term. We can also relate this to the derivative. If C sub n is f of n, then we can check that f prime of n is negative. Right? That's another way to determine if a sequence is decreasing. Right? We look at the derivative of that kind of C sub n. Okay, let's go through some examples here. The first is the series from 1 to infinity of minus 1 to the n plus 1 divided by n. Okay, and I want to write out a couple terms here. So when I do that, I'm going through my stepping through. When n is 1, I have 1. When n is 2, I have minus 1/2. When n is 3, I have plus 1/3. When n is 4, I have minus 1/4, plus 1/5. Then when n is 5, so on and so forth. Okay, and we can quickly see that this is an alternating series, right? Every term is the opposite sign of the previous and the next, so on and so forth. So that's where we see the alternating part. I'm going to use the alternating series test, but for that, I have to extract what C sub n is. And remember, c sub n doesn't deal with the minus 1 part. So I'm going to step that off to the side, minus 1 to the n plus 1. And then what's left is just this 1 over n. That 1 over n is our c sub n. So that's what I'm going to take the limit of and then the derivative of, or check whether it's decreasing, of that c sub n, okay, in my alternating series test. So first here I take a limit. The limit as n goes to infinity of c sub n is the limit as n goes to infinity of 1 over n, and that's of course 0. That's an easy, quick one. Sometimes they're a little bit more involved, but in this case that was really straightforward. Number 2 is that c sub n plus 1 has to be less than c sub n, right? The next term in the sequence has to be smaller than the previous. It means decreasing. So what I do is I replace n with n plus 1. So c sub n plus 1 is actually 1 over n plus 1. And c sub n is just 1 over n. So I've written this inequality here. I have to kind of check that it's true, okay? We can basically do that for free here, right? Because the c sub n plus 1, 1 over n plus 1, has a larger denominator. It's a smaller fraction than 1 over n. We can also multiply through and see what happens here. If I cross multiply, I have n on the left is less than n plus 1. And that's of course true, right? N is smaller than n plus 1. Yeah, that's true. This is a decreasing sequence. You can of course take a derivative as well. This is enough, and it's quick for the most part to check. In this case, that piecewise that it's decreasing, term by term. Oh, here's my derivative. My function is 1 over n. Its derivative is minus 1 over n squared, and that's of course negative, right? N squared is positive. So both of my conditions are met. Therefore, by the alternating series test, AST, the series minus 1 to the n plus 1 converges. That's it. It's usually a pretty quick test, and it's usually pretty easy to determine that you have an alternating series. Okay, let's do another one. I have n divided by minus 2 to the n minus 1. This one's a little bit more tricky. The minus 1 or minus 2 to the n minus 1, that's probably going to be the bit that's alternating, right? They're creating a switching sign. When n is 1 here, let's go out a couple terms. When n is 1, I get 1. And when n is 2, then I see 2 over minus 2 to the first, plus, when n is 3, I get 3 over minus 2 squared, so on and so forth. And I'm going to simplify some of these here. The first one is 1. The second one is a minus 1. Those two are going to cancel. That's okay. Where there, I'm just trying to see which test I need to use here. 3 over negative 2 squared is a positive 4. Minus 4, that minus comes from negative 2 cubed is a negative 8. The next term should be 5 over positive 16, then minus 6 over 32. Indeed, I have an alternating series here. All right. From one term to the next, I have a switching sign. Okay. So that means I can use my alternating series test, but to do that, I need to be able to extract c sub n from this a sub n here. So what I do is I kind of pull off the part that's that minus 1 to the n, and it's kind of hidden here. In the numerator, I have n. In the denominator, negative 2 to the n minus 1 is the same thing as minus 1 to the n minus 1, and then 2 to the n minus 1, right? That's raising both minus 1 and 2 to the n minus 1 power, okay? So it's a little bit of algebra there. Now this, excuse me, this minus 1 to the n minus 1, I can bring that up to the numerator, right? That's creating a negative in the denominator, but a negative in the denominator is no different than a negative out front or in the numerator. So I'm going to take this guy here, and I'm just going to put it kind of off to the side. N over 2 to the n minus 1 then is my c sub n. There it is. So everything I do will then be to c sub n here. I have to take a limit and then maybe a derivative or to check whether that guy is decreasing. So my limit here, the limit of c sub n as n goes to infinity, is that guy there. And I can do L'Hopital's here because both numerator and denominator are approaching infinity. Okay? Derivative of n in the numerator is 1 divided by derivative of 2 to the n. That's that tricky one. It's like 2 to the x. 2 to the x minus 1 should be 2 to the x minus 1 or n minus 1, natural log of 2, natural log of the base. Okay? And as n goes to infinity, the only n there is in the denominator now. Denominator is growing without bound. It goes to infinity. The fraction then goes to 0. Okay. So now, to check if I have a decreasing sequence. Okay. It's not enough to just say, oh, the limit's 0. It's got to be decreasing as well. We also have to check number 2 here, that it's decreasing. I can come up with a sequence that's approaching 0 that's not decreasing. Okay. So what happens is I check c sub n plus 1. I plug in n plus 1 for n. So in the top I have n plus 1. In the bottom, 2 to the n minus 1 plus 1 will be 2 to the n. I want to check that that is less than the nth term, or c sub n there. And again, I'm going to do this cross multiply thing. On the left, I'm going to have an n plus 1. And on the right of that inequality there, I'm going to have an n times 2 to the n divided by 2 to the n minus 1. Those are like bases, so the powers subtract because I'm dividing terms with like bases. So that's n minus a negative 1 is n minus n plus 1. On the right, I have n plus 1 is less than 2n. Okay? And that's, of course, true. When n is 1, I have 2 is less than 2. So actually this is true for n bigger than 1, right? Which is okay. But everything on the right-hand side is going to be larger after n being 1. So I'm good to go for my alternating series test. What I have is then, getting ahead of myself. I can also take the derivative here. That might be a little bit easier. I would have to do quotient rule, but what I get when I simplify is 1 minus n natural log of 2 over 2 to the n minus 1, and that we can show is negative as well. So sometimes it's easier to take a derivative, sometimes it's not. I just want you to know that you have the choice there. You can take a derivative and show it's negative, or look at this kind of term-by-term comparison to see that you have a decreasing sequence. Both of our criteria are met, so by the alternating series test, AST, our series n over negative 2 to the n minus 1 converges. Okay. So there's 2 in a row where we have convergent alternating series. Not all alternating series converge, right? So here's just an example. It's a quick one. Minus 3 to the n. That's a geometric series, right? And we can show very quickly that this guy does indeed diverge. Well, look what happens when I go out term by term. I get 1, then negative 3, or minus 3, plus 9, minus 27, so on and so forth. All right? There's my c sub n if I were to treat this like an alternating series. But c sub n, 3 to the n, that's increasing, right? I'm increasing powers of 3 here. I'm going up by a power of 3 every time. This is not a decreasing sequence. The c sub n there is not going to go to 0. We cannot apply the alternating series test. AST does not apply here. Though it's an alternating series, it doesn't meet my criteria. In fact, like I said before, because this is geometric, we can quickly show that it diverges, but also from the nth term test, we can show that this guy diverges. The limit as n goes to infinity of minus 3 to the n just does not exist, right? It's growing and it's switching from negative to positive, positive to negative. There's not a concrete limit there. We can say that this limit is not 0, therefore the series converges. So there's multiple different ways that you can argue that the series there diverges. I just wanted to show a quick example of an alternating series where you can't just go right to the test and say it converges, right? It just depends on what you got. Okay? There'll be another video in this section. Thanks for watching.